Okay, we'll be starting soon. Am I audible? Could someone clarify if I'm audible? Am I audible? Hello? Okay, so yeah, that's yeah. Okay, so today's topic is like we're gonna learn about GOT override exploit. So whatever we did in the previous session, it was to lead up to this. Yeah, so the basic idea of the exploit is we have to find the .got.plt address of a particular function. Remember last time we saw lazy binding. The first time when the function is called, the GOT entry doesn't have its address initially, but the second time it's called, it gets resolved and it's put into the GOT entry. So the next time when it's called, it directly goes to libc. Yeah. So we need to find the actual the got.plt address of a function first. So say we have puts. So puts at got.plt, that address we need to find. Okay, and the next part of the exploit is find the new address of a function you want to call instead. So there are two cases in this. One is if within our C code, let's say we have one main function and we have another win function inside, which either has the flag or it. Uh, so there's another win function inside. It has a flag or it spawns a shell, either of these two. So we can replay, we find this. So this is the function we want to call instead of whatever functions are being called right now. And the second thing is, like we will directly call system /bin/sh from libc. It is we are spawning, we're ourselves spawning the shell. Okay. And the third part of this exploit is creating the payload which will write into the GOT. Okay, so let's go into each of these. So getting the .got.plt address. We can use pawn tools or if like okay, pawn tools andGhydra or any other reverse engineering tools to find the .got.plt address of a particular function. So this is an example of how to do it. Like from pawn import star, that's the first line. We do this context.binary. We try to get all the symbols of our ELF file. I think in the last session I showed you guys that an ELF file in its header, if it's not stripped, it has certain information. It has all the symbols, names of the functions that are inside it, names of other um, functions and entries in the other tables, like the GOT table, the GOT.plt table. All that information is there with the binary when it's not stripped, when it still has its um, symbols intact. Yeah, so we're basically loading all those symbols using pawn tools, getting all those symbols, and using that we're getting it. So um, we're doing so wait, something is equal to elf of that binary. So this is the syntax: context.binary is equal to binary, and then you open your file with that, whatever your file name is, and then you take out the elf symbols from it, the ELF of the binary, and here we're turning off checksec. Otherwise, even if it's on, then you get to see all the protections that are there for the binary. Yeah. And then how we get the GOT entry is, now we have all our elf symbols. So vuln underscore elf dot GOT dot whatever function. So if it's puts, it'll be dot GOT dot puts. That's how you get the address. That's using pawn tools. You can also get it on Hydra. You can also get it using GDB and some attachment to it like Jeff or I think PEDA. Those things, they're also pretty useful. You can get your um, GOT addresses with that. And another thing, it works here because our ELF file is not position independent. Okay, so that's why the addresses will be constant and they're same every time. Okay, yeah, that's what's explained in the next slide. So pi being off, note that this leaking of addresses using pawn tools or Ghidra only works if pi is off because yeah, so pawn and Ghidra internally run the executables. They run the executable in their own virtual machine, and the symbols that they get are from the the instance of running it on their own virtual machines. So if pi were on, the addresses would be different on our own device and on pawn using pawn tools or using Hydra or anything else. You get different addresses, but because pi is off, that's why we can use pawn tools to get the address. This only works when there's no pi. Yeah. Yeah, on Ghidra, I think if pi is on, we still get just the, like considering zero base, all the addresses will just be written as offsets. So you get some address, but it won't be very useful. Okay, then we go to the next part of our this thing. When we find the new address of a function you want to call, the second step. So under that, the first thing is a local win function. So yeah, if there's another function inside your C code with like there's the main function, if there's another function, the win function, which has a flag, which has the flag inside it, or if it has a shell and then you use the shell to access the flag. So that's when there's a local win function. When you're not using addresses, you're not using functions directly from libc. You already have a local function which you just have to execute. So that that's one way you can do this exploit. The second one is if you don't have a win function within the executable, then you'll be using libc. So you have to how in the seventh session, I think, read to libc exploit, you would have had to figure out the version of libc. Then usually ASLR will be on, so then you have to find out the offsets of all the functions, and using the offsets then you determine the address of system. There it's exactly the same as that, but there we did that using ROP chains. Here we won't be using ROP chains. Instead, we'll be writing the address in the GOT place. So like we'll just go through the slides and then I'll show you a demonstration of this. Yeah. So we need to find the address of system and /bin/sh using offsets. Yeah, and that's necessary when ASLR is on. Okay. So how do we, then now coming to the last part of the exploit where we write down, so after we found the address of system, we need to write that down. So how do we write it? There's a special format string specifier, percentage %n, and like all the other format string specifiers in printf, they are used to print stuff, but this doesn't print anything, and instead it writes, and it's like it's quite questionable why it even exists, but yeah, it's useful, we use it. So this format specifier, it takes one parameter, that is, it takes the address into which we need to write. So it takes a parameter, and what it writes into it is the number of bytes that have been printed so far. So if there are, say, n bytes printed, and then you have a percentage n, and then you provide an address where you want to write it to. So you would provide an address with this dollar, like some number and a dollar sign. So that's that position we want to write it into, the address present at that position. Okay, we'll go through it slowly. I know it's a bit confusing. But basically, it takes one parameter of an address, and it uh, also, sorry, it takes one parameter and it writes the number of bytes that have been printed so far. These are the two most important things. We'll go into it slowly. So here's an example. There's percentage 20x, percentage 7 dollar n plus an address P64 pawn tool packing it into 64-bit way. I think it's mostly little Indian. Yeah, and GOT puts. So this is the address that we had, and so it writes into the address present here. So what happens is we have a stack. 1 second, I'll just connect my audio silence to it. Yeah. Yeah. Okay, so we have a stack, okay, and this is probably the RBP, the base of the stack, and yeah, a lot of stuff are there on the stack. What we're doing is we are first using pawn tools to get a particular address, to get address of say puts at got.plt. Okay, so we have this address. Let's yeah. What we're doing is we're now placing this on the stack using a buffer. Okay, we're passing that as our input and we're placing it on the stack. Okay, so right now this address is here. Now, after that, there's our percentage n, right? Percentage n. So what we're doing is we're calling the particular input that leads up to that. So say t and leads up to that. So then we're finally pointing it at this location. That's the location at which our address is placed, and it doesn't write it here, it writes it at the address that's mentioned here. So this points it to this points it to the GOT table, and so we replace the address that's present there and we overwrite it. Yeah. It'll make, like, we'll show a demonstration, so it'll all make sense then. This is just an overview. Okay, so GOT underscore P puts is the address of puts at GOT.plt in the is the address into which new values are written. Yeah. Then the 7 indicates the 7th entry as per the calling convention. We will discuss the calling convention too. And 20x, yeah. This basically prints 20 characters and thus writes 20 into the new address. So if you have okay, I'll probably show that also in a demonstration. So, so like basically now we're writing 20 into this address. So, 20x, yeah, percentage 20x. It's not percentage $20x. That would be different. Okay. So remember, there's no dollar here. And percentage something 7. Let's just continue with $7 n. It basically writes 20 into this address that it points to. Yeah. So how many ever? Yeah, that's it. Okay, now there are two important format string specifiers. So percentage n is for writing. It takes a reference. Okay, let's go with all the format string specifiers one by one. You've probably come across percentage p, percentage x in a previous exploits. Yeah. Percentage S is a very important one for this specific case. I'll tell you why. And percentage N also. So I literally spent 2 days finding out percentage S, like which format specifier could be used for leaking values. So it's very useful, percentage S, and I didn't know it before. So yeah, um, these two speciality is that they take a reference, so they either read from the address present there or they write to the address present there. They don't read, like if I had percentage p, I'll give you, oh god, how did I move before? Okay, no. Yeah. Okay, so yeah, if I had percentage $7 P versus percentage $7 S. What's the difference? Both of these print some value. So if you pass this through a printf, you'll be printing some value. So what happens is, say this is our calling convention, and the first entry, second entry, third entry, fourth entry, fifth entry, sixth, and seventh. But I'm assuming you guys know basics of format string specifiers. Yeah. So anyway, this so I go to the seventh entry. Yeah, let's say this has some address in it. Okay. What the first one will do is it will directly print the address. It prints that value located at the seventh position as per the calling convention. The second one, it'll print, so this address points to a certain value. So this is going to print that value. So it takes in a parameter as a reference. This takes in that parameter as the value itself. That's it. That is exactly what it prints out. That's a percentage S is very, very, very useful. Okay. So percentage N for writing, and same way, percentage N also writes. Like, so if I had percentage N here, percentage $7 N, this is the seventh entry, by the way. It now writes into that address, not at the seventh position. Okay. Now, okay, this is a special formula which we'll be using later. We'll get back to this. Strings are not, yeah, another note is strings are not terminated. I will explain why again. So this is very important too. You have to reorder certain things so that you don't terminate your string beforehand itself. Maybe your address has multiple per backslash x00. So by little endian, it'll split the entire address into bytes, like so into two digit things. So whenever you get a 00, it might terminate the string there itself. It won't read whatever is there after that. So you need to be very careful with that too for writing. So whenever using format string specifiers, these things become very important. Okay. So coming to the calling convention, we're talking about x86 convention and 64-bit. So your first, like, the first thing that it calls will be RDI, then RSI, then RDX, RCX, R8, R9, and then comes the stack. So if I do percentage P, it prints whatever is there on RSI, on this, what do you call them? Oh God, what are they called again? Register, yeah, yeah. Register. Okay. So it'll print whatever's there on RSI on this register. Then the second, if I do like if I do two percentage P's, it'll print whatever's on the second one. Three of them, so it'll print the first one RSI, second one on the RDX, then third RCX. So I keep printing a few till I get to the stack. Okay, the sixth one is from where the stack begins. I start printing out inputs on the stack. So the best way to find out from where will you start getting the thing or from where does it start reading is you put in some A's and then you put multiple percentage P's or percentage X, whatever, multiple of them. Or actually, instead of, because this is 64-bit, all your addresses will be 8 bytes long, so we can put LX, multiple LX. Yeah. So what this will do is in the output, it'll first print AAAA, then it'll print some multiple gibberish addresses, okay, a lot of them. Till you again get to some place where you have 41414141, and so you know which entry. So you count 1, 2, 3, 4, and then the nth entry now has 4141. So you know from where onwards do things start getting put onto the stack. So that's the way you identify it. Yeah, we'll do a demonstration. Everything will get clear then. Okay, when do we use overwriting GOT attack instead of rob chains? Now this is where we come to the point. Like if we have rob chains, why can't we just do that? And they're much more powerful than writing onto GOT because here you're only able to write like something into an address. You can't you can actually do a lot of like it's much more difficult actually because you need to write so many bytes into it. It's a little more calculated and all that. So it like you only do this over doing just rob chains is when you can't do rob chains. And when does that happen? Rob chains are usually possible if we can reach the base of the stack and place new instructions there. If the user input has a restricted size which cannot overflow the stack. Okay. So what does this mean? Yeah. So this is our stack. Okay. So this is the first thing on the stack. Okay. It, yeah, this is where the stack begins. So from somewhere I now called main, say. So what happens is we first push the address of the line just after it. So like say this is from some place, I called it. Whatever the line is after that, we push that address here first. Then we push RBP. Then we shift the stack pointer to some place. Then we create buffers, and then when the buffers fill, they start filling this way. So we can overflow the stack. Then we overflow over this like so. What happens is after the entire function is like after we reach the end of main, say main and it has a lot of instructions in it. You do a lot of things. When you come to that return 0 or say you have exit whatever, in those cases, like the stack pointer goes back to the top and then the RBP is popped and then the instruction just above it, that's the return address. That is just the line after the place from which it was called that gets executed and we return back to from where it was called. So what we do in rob chains is we overwrite this entire thing and then we put our own instructions there so that those instructions start getting executed. Okay. What happens in this case where we can't do rob chains is say this is our stack, this is our BP. We've created a buffer which starts taking inputs from here. But in our read statement, so what does read have? It has the parameter from where it's reading, which is standard input output, then into what it's reading. So let's say it's reading into buffer and the size. Say the size is smaller than the amount that's present here. Okay, say it only allows it to read till this much, then we can never get to the base of the stack. We can't override those addresses and we can't do anything here. So in that case, where off chains are not possible, that's when overwriting GOT becomes very uh, like that's the only way you can get through it. Yeah. Also, another thing in this percentage n thing, we're writing some address into it, right? So if we write an address which doesn't exist, we'll get a segmentation fault. So yeah, now we'll go to the demonstration. So for this, I'm using a try hack me question in the like from the pawn series, the pawn 108, the eighth one there. So okay, so first I'll just run the question. Yeah. So in the question, we see that I'll just take it to the whiteboard. Yeah. So also I didn't show you yeah, we'll do all that. Okay. From the previous lecture, the demo didn't work, right? So I have it ready this time. I'll be able to show you what I was talking about by, the first time it doesn't right, the second time then the GOT entry is filled and it directly goes to libc. Daisy binding, basically. I'll show you that. Okay. So let's check out what this does. Yeah, and then it says registration number, something, I don't know. Yeah. And then it prints this out. Okay, so we run it again and we'll see if it has format string vulnerabilities. So percentage %p, yeah, and the second one also. So name doesn't have a format string vulnerability. It directly just prints out percentage %p. It doesn't give us any addresses, but the second one does. So the first it prints two addresses. So second one is a nil address. So we can see it prints out two addresses. So the second thing has format string vulnerabilities. Okay. Now I've already created the exploit for this, but I'll be explaining what we do in it. Just like in every line. Okay, also we'll do the demonstration first. So GDB, yeah, Jeff is working. So I'm gonna disassemble main first. Yeah, let's just look at it. So yeah, as I told you that time, first RPP gets pushed onto the stack, then RSP gets moved to the position of RPP, then RSP gets shifted down by some amount, 90 bytes here. I think, yeah. Okay, shifted down, and then everything else starts. Here, the canary is being filled. So next line is how the canary is being filled. Okay. So then we see that, see when puts is being called, look at +56, that line. Puts, so we don't call puts directly, we call puts at PLT. And then again. Now here in this setup and banner, actually puts have already been called before. So I won't be able to show it to you properly for the first time call. Instead, I'll go to printf. Printf has never been called. So we put breakpoints here. Okay, and then we put okay, we also have a read. I think read is also not called for the first time here. We'll find out. Hmm. And then the next line again. Now the second printf is being called. So we want to call it twice to see exactly what's happening. Yeah, and then our fourth breakpoint is for the second read. Yeah. Okay, so now we will run it. Oh. Okay, let's see why not. Printf. Okay, wait, I'll just do it again. Yeah. Okay. So we hit our first breakpoint, the first printf. Okay. So we'll just step into it. Okay. Look here. Can you guys can see the highlighted part? Yeah. So see, right now I'm at this line, call printf at plt. Then we see just the next line says jump to printf at got.plt. Then okay, then we see what's under printf at plt. Okay, so I'll just step to this. Yeah. So now we're going to step into printf at got.plt. That is going to be called in this green highlighted line. Can you see that? Yeah. Okay, again. Okay, now we are here. Hmm. Okay, I'll tell you what happened here. So we went to printf at got.plt. That didn't have the address, and the address there was the address of the next line on the PLT table. So it jumped back to the PLT table. Then we pushed 3 onto it to tell the disassembler what exactly we want to resolve. Okay, and then now the next line is going to resolve it. It's going to jump to that. So yeah. Look at this. Okay, so DL runtime resolve. Yeah, so now it's resolving it. Okay, can you see these addresses? Okay, now we'll also see what exactly this address belongs to. I think uh, VM map. Yeah. Okay, so this. Yeah. See this red one? Those addresses belong in this interval. FFFF 7FC 5 yeah, it's somewhere in between these two. So 7FE, that's 7FD. Yeah. So between C and E. Yeah. And this is like this is the resolver. So like it belongs like this address basically we can be sure now that it's the resolver's address and the linker's address because it's pointing here. Okay, now we'll continue and we'll see what happens in the next line. Okay, now we hit the second breakpoint. Let's step into it. Okay, so again, we're calling printf at got.plt. Let's see what happens now. It directly goes to printf. Look at this. It doesn't have to resolve it again. So it directly goes there. And yeah, so this is demonstrating the first time it has to resolve it. Then it writes down the address in got.plt. The second time we run it, it's already written there, so it directly goes to the printf and libc. Again, we'll check where this address is by VM map. We'll see. So 7C606F0. So yeah, it's here. It's again in the same place. It's an actual libc. Okay, so yeah. Okay, that's all about this. I'll just quit. Yeah. Okay, so I'll show you the exploit. Okay, so yeah. I also wanted to show you like just show it to you on Ghidra. So yeah. So I already have it open here and I had already analyzed it. So it'll take less time to open. Oh, yeah. Okay, so under functions, we'll first go look at what's happening in this question. So main, yeah, found main. So okay, so first, and also we can see the disassembly on the left with along with it. So this part is basically putting the canary. Yeah. Then you get to see that yeah, RSP shifted by 90 down. So 90 bytes it goes down. Wait, we keep track of it all with a diagram. So this stack, we first pushed in our RBP. Okay. Then we put then okay, our RBP basically points here. It's yeah, it's pointing to this. Then RSP was initially pointing to that. Then we shifted it 90 below. From here, it was pointing to RBP. We shifted it 90, not 9, like not 90, like 16 into 9. Yeah. Yeah. Now RSP points somewhere here. Okay. Okay. Yeah, then this part we put the canary, then okay, then we call setup, we call banner, then we puts another puts, then comes printf. No, we have a read after the yeah. Read is what's important. So your external read. Yeah, local 98. Local 98 is stack minus 98. So local 98 is here only. Um, I'm sorry, I'm saying 98. It's not really 98. It's 9 into 16 plus 8. So this is the top of the stack. RBP is at minus 0x8. And this is um, minus 0x90. So the buffer is also located here. Minus 0x98. It starts taking in values, it goes this way. Okay, this is the first one, the first read, and it only reads 0x12. So that is 18. It only reads 18 things from here. So the first thing that we have, remember the first one was asking for a name. So it goes up by 0x12, which is around 80. Okay, which is 80. Then the next read, again it reads from 0x78. That's the second buffer, and it reads 100 stuff. Yeah. Wait a second. So 20 things below. So somewhere here, and a lot of stuff. Yeah. Oh, oh, 100. 100, we have to convert to hexadecimal. 16 nines are 96, right? So 90 4. Yeah, that's also more than that. 16, sorry, 16, 6 are 96. Yeah, so 64. So it doesn't reach the top of the stack. So right now we're somewhere here, which is at 0x78 from the base of the stack. Oh God, I'm so sorry. Yeah, and it fills upward only 0x64. So it doesn't reach the top. Okay, it can't reach the top. Yeah. That's the second read. The second read, which takes the registration number, the one which had format string vulnerabilities. Now we're also going to look at why does the first one not have format string vulnerabilities? Why does the second one have? The first read. So it reads something into this guy and printf. Okay. Yeah, wait, we will see. Puts. Okay, so the first one is name. It's called by a parameter percentage %s, and then we put local 98. So it's not directly called inside a printf. But the registration number is directly called inside a printf, so it has a format string vulnerability here. Yeah, I hope you're able to understand that. Name and then this is called again by a format string. So it's not directly calling, it's not printf and local 98 inside brackets. Sorry, here. But this one is printf local 78 directly inside the brackets. So that's why this has a format string vulnerability. Okay, so now we look at the PLT and the GOT table. So if you had been looking at this part here, see there's GOT.plt, and then also there's sorry, yeah. So just the .plt table, yeah, PLT section. Okay, and then under that we have puts, and then we have stack check fail. That is the canary check fail. That function's also there. Then system. Okay, system is there here, which is cool. We're not going to use it. Printf, read, like that. Okay, now each of these again point to the where is that? Okay, now we're going to look at the GOT.plt. Yeah. Global offset table. Here you have puts, stack check fail, system, printf, read. Yeah. Also notice puts was I think 0. This is 1, 2. Printf is 3. So when we go back to PLT, yeah, PLT when we see puts see we're pushing 0. Then for stack check fail we're pushing 1, pushing 2. So it has its own mapping internally that each function it has mapped. So each function has a different number. So when we're calling printf, when it wants to make the resolve it, it pushes an integer 3 onto the onto that part of the stack, and it does this, and then it calls the external thing. Yeah. Okay. So we want to, so the first part of our exploit was what? It was to, basic idea was to find the GOT.plt address. So we can even do it withghydra. So we go to GOT.plt and we want to overwrite puts. Okay, that's we want to overwrite puts. So we can get, so here's the address. that we need to change. Okay. Yeah. Now let's just do it in the with using pawn tools. You don't need all that. We can just do it with pawn tools. So from pawn import star, then context.binary is equal to binary, and then our file name. Put that in there. Then this is just a name is equal to elf binary, and we're turning off checksec. So we first loaded the binary, and then we are pulling out the symbols from the binary and all the, yeah, basically the symbols on the binary. Okay, and okay, here I have written a discovery that I had while getting it, that the 10th position of the register number is where the input starts being put onto the stack. So let's demonstrate this. How did I get it? CD, think minus, yeah. Okay, so another trick, CD minus takes you to the old place where you came from, in case you didn't know that. Okay, cool. Yeah, now I want to just run the program and find out which position on the stack, that 10th thing that I told you, what does that mean? Okay, so 1, 2, 3. Okay, now and then I put multiple percentage LX. And then I can use a separator so that I can clearly see the difference between the different addresses. Okay, so yeah, this is what I'm talking about, this entry. So A, and then our first address, second address, the 0, third address, fourth address, fifth address, and then we see so many AAAs. Wait a second. No, I think this one is from the previous thing. This AAA that had been put onto it. Okay. We count again. Wait, okay, so I should not use A's. Yeah, again, here I can see some more gibberish, and then again 41, 41, 41, which is another few A's. So let's count 1, 2, 3, 8, 9, 10. This is the 10th one. Okay, so the first thing is our long AAAA thing that we had here. So we'll just verify that again. So say I have that, and I get this. What am I doing? I get this. And I change this part to. Okay, I can't go. Shit. Sorry from my language. Okay, so it kind of stops after the point. Okay, that was a bad demonstration. I'll just do it again. Yeah. Okay, so ABCD, and then first address, second address, third address, fourth, fifth, sixth, lot of A's, seventh, eighth, ninth, 10th one. You see 4, 4, 4, 3, 4, 2, 4, 1, which is A, B, C, D. They're in little Indian, so that's why they're flipped around, but we can see it's here, and it's at the 10th position. So from the 10th position on the stack, do I start putting in my input for the second thing? And we can also calculate this from the diagram that we had made before. Where is that? Here. Um, 7, 8. And we saw that RSP was at 9, 8. So that's another 20 things away, 0x20. And our each of these 64-bit addresses are 8 bytes long. So 20 is what? 20 is 32. Yeah. So 32. So that's 4 addresses. And we start like through the calling convention, we saw that it's 6 of them and then whatever else. Right, so 6 and then the sixth one is on the stack, then uh, 4 more. So the 10th one is this. Yeah. I'll show you on the calling convention. I'll show it again. So we don't need it, we don't need to do it this way. We can actually calculate it also. It's very logical. So look at this. So this is not counted. We start from RSI. First, can I highlight? First, second, third, fourth, fifth. Sixth one is on the stack. So this is the first one on the stack. 6, 7 is the second one. 8 is the third one. 9 is the fourth one. And then we have our this input. So 4 entries later, after 4 entries, I'm like so till 4 entries, I'm done till here, and then the second buffer starts filling. So that's the 10th entry. Okay. Okay, coming to our exploit now. So that's how we figured out that it's the 10th position on the stack. So there are multiple ways of figuring that out also. You can do it by brute force, the first one that I showed you, or you can properly calculate it. Okay, then another thing, I found that the padding was 12, that is 18, because the first one only takes in 18 input, right? Um, so till here 0x12. Yeah, that's why I passed in the entire, all of those are passed A's. Even if I don't do that, it doesn't make any difference. So if I just pass a single A, it's not going to cause any difference. My exploit is going to be exactly the same. Okay, so we passed that first one, done. Now we get the the GOT address of puts. So that's the first thing we do. And I'm just printing them out to see if it's the same. So I printed these two out to see, and this is what I got from GHydra, and this is what I got from um, using my, and like I'm printing out this thing that I got from Pawn, and I just checked if they're the same. Okay, yeah, now let's go back to GHydra and analyze the question a bit more. So main, yeah. So we saw that we are not able to reach the top of the stack, so we can't do rob chains. So if we're supposed to look for if there are any other functions within our binary which have any kind of win function. So there's this thing called holidays. If we see that, so holidays spawns a shell. So what we need to do is we need to call holidays somehow. And our main function doesn't call it in any way, doesn't have any directory of calling holidays. It's not there anywhere. Just a lot of printfs and puts and no function calls. Yeah. So so now we figured out that if we can change one of these functions, say these puts and all that, if we can change one of these to holidays, like in the GOT entry, instead of actually calling puts in libc, if it calls holidays in our binary, then we're done, right? We win. So uh, puts or anything else, printf, something. It's one of these functions after we have changed it, after we've changed it, the next time one of these things are called, if they can change it, that's great. So looking at our first one, printf read, yeah, this read, this is where we're going to be putting our percentage and format string thing, and we're going to change it. So whatever functions are there after that, um, after all this, printf local 98. So that's when all those changes will happen. This is the place where that the format string, whatever input we gave, is actually going to run. So after this point, there's a printf and there are puts. So either printf or puts, if we change these functions to holidays, we're done. Go look at holidays once. And let's see what are the functions called within it. So holidays itself calls a printf. So if we had changed printf to holidays, and then when it comes across the next printf, it'll again it'll again do holidays, so it'll keep going in a loop. So we don't want that, and it'll never really reach to the next line. It won't reach to system slash bin slash sh. Okay, this is where system was defined. Anyway, it doesn't reach this, it just keeps going in a loop. It gets into holidays, it reaches up to here, and again this is another call for holidays, so it'll keep going in loop. It won't reach system. So we don't want to change printf to holidays. Instead, we'll change puts to holidays. Yeah, we had two options here, but printf is making it into a loop. Puts will do the job, so we'll do puts. Or actually, we can even change stack check fail. But yeah, yeah, we could actually do that. Okay, anyway, but I decided to do for puts in this. Okay, so now I'm trying to find holidays, the address of holidays. So let's go back to Jihadra. Let's go to holidays. Okay, let's go to our this. So this is the starting address for holidays 0040123B. Yeah. So I need to get this address. I can either directly get it from Jihadra and put it there, or even Jeff and GDB can also give it to me. But how do I get it? Through pawn tools. Uh, so vuln.elf.symbols, and then you put your function name that gives you that. Okay, I'll probably put screenshots of the recording is there. Yeah. So vuln_elf.symbols, and then you have this. So this gives you the address of holidays, and I printed it. And then I tried to see which format is best for me. Which format do I get it into? Like you just get to get an idea. So I changed it into a few things, and I printed all of them. And yeah. First one, I just did one. I got the symbol itself in the way that it gives it initially. Then I made it into a hex string. Then I converted it into an integer, a hexadecimal integer. Yeah, and then yeah. So I got. Now let's talk about. Then I did something here. I divided, and then I floor divided and found the remainder. So I'll tell you why I did this part. So this was the initial payload that was there. Then I changed the payload. So I have two, the other payload also works, but I have two payloads which work, and I'll show you what exactly I did. So in this one, you see, I have put in values 64x and here 4603x. I put in values. These are decimal values. I said in that one I had put 20. Let's show that to you again. Yeah, this 20, basically that number. So that many bytes are being printed. So in this one, I've manually done it, manually got the number because I got the address from Jihadra directly, and then I calculated it manually. But I didn't want to do that because I wanted to see how to do it, like if it means the same thing, and then get it to this. So, okay, there are a few things to explain here. Why have I split it into 2%, like two n things? Why am I writing it into two different parts? And why pointing to addresses and doing that? Why not just in one thing? So let's go to GOT. Yeah, it's a GOT.PLT. No, let's go here. Okay. Puts, yeah. So 00400018. This is what I want to overwrite. Now, percentage n will naturally override the size of an integer, which is 4 bytes long. But these addresses are 8 bytes long. And see, the first two bytes are 00. So that's not an issue. The ones after that, so 00, or actually the last two little endians, so they go right to the end. But anyway, so 40 and 4018. So six six bytes are what I want to. Actually, this is too tiny. Um, yeah, I want to override six of these digits, not eight of them. And my percentage n just overrides four of them. So I can either convert my percentage n to a long int, which will write eight. But when I do that, I will have to do percentage a huge number x, like a 8-digit number, which is huge, and percentage $7 x, whatever. Here 10 actually, because the 10th one is the first, or the 11th one, whatever. So this is very big, and whatever I print here, it actually prints all those empty characters, and then it does the rest of the exploit. So if I directly run my exploit, you see there's a huge gap, and then it continues. It's because it has printed so many digits onto our screen. So to uh, like to prevent a huge printing to happen, which will take a long time to load, what we do is, say we split it into two 4-digit numbers. The overall number is smaller, right, than one 8-digit number. Obviously, you get that. So this is still like one big 4-digit number, maybe, or maximum 5 digits. This is still an 8-digit number. So the number overall is lesser. So that's why we split it into two parts and do it. So in our address, there's 00 and 404018, 404018, or whatever. Like these two are not going to be changed. What is it? Uh, backslash x, whatever, or 0x, and then all that. Yeah. So what we'll do is we first change these four, and then we'll change this. Okay. So so if we're basically shifting this is a 4 byte integer, so we're shifting it by 2 bytes. So we're going to go to puts at got.plt plus 2. Okay, that's the first thing. And this is still at puts at got.plt itself, but it's just a 2 byte long thing. So that's a short integer, which is h n, I think. Half integer. We write it with h. Yeah. Okay. So yeah, let's go back and look at our exploit. Okay, wait. Actually, I want to explain one more thing. So now I realize that the 10th entry onwards, it takes in inputs. So uh, percentage some number n, and then I write some percentage some number x, that is the number that I want to print there. This is my first bit binary bit string, I think it's bit string, yeah. Then p64 something, the address got puts. Okay, yeah. This is automatically a bit string. I think it's a bit string. Okay, so look at the number of characters here. See, this is 64. So 1, 2, 3, 4, 5. and say this is the 10th position, 11th. And this is 9. So on our stack, things are still printed as 8-byte long things. And also these pointing things is $1, $2, and then $11. These basically point to 8-byte long addresses. Okay, so first 8 bytes, this points to the second 8 bytes, this points to the third, like the 11th set of 8 bytes. So basically, so that we put this address onto a proper one of these intervals of 8 bytes. This has 9 things now. It's not, it's 9. So we're going to add 7 more things to pad it, so that now this is the 10th entry, then this much will be the 11th entry, and then this is the 12th entry, so that it reads from the 12th entry. So it'll be bit string percentage, say 64. That'll be different, whatever number we want to print. So not the 10th, not the 11th, but the 12th entry. $12 N, and then we add another 7 A's, 3, 4, 5, 6, 7, plus P64. So the 12th entry is this. GOT puts, yeah. So what this will do is so till here is the 10th entry on the stack of this buffer, 11th entry, and this is the 12th, 8-bit long 12th entry. So it'll point to the 12th entry. So then it points to this address, and so it goes to the GOT table and overwrites it. Yeah. Coming back to the exploit. Okay, we'll first look at this payload. This is also a proper working payload. I'll run it and show you, because I've calculated this manually. So some number I've printed, then this next one I've printed another. So this is the first percentage n, that is the 4-byte long thing. Then I printed another number, another thing that I need to write onto it, and then our half int. That's what I'm printing. And then this is pointing. So this is the 10th entry, the 10th entry. This is the 11th entry, followed by the 12th entry. This is 13, and this is 14. So my first one points towards the 13th thing on the stack. You see 13 there? 13. And this points to the 14th entry onto the stack. That is this address. Yeah. We calculated it. I showed it to you here. Where? Oh, where did I write it? Yeah, here. Yeah. This is at the address +2, and this is at just the address. Half string is at just the address, and the full half integers are just the address, and the full integer is our address +2, which is what we have here. The 13th one, which is the full integers pointing to the address +2, and the half integer, where is that half integer, is pointing to the 14th entry, which is just the address. Okay, now we need to figure out what number you want to write on it. What do we want to overwrite it with? So we have to find holidays address for that. So again, go back to JHydra, find holidays. What's holidays here? Yeah. Then this is the address 0040123B. Okay. So we'll do some math here. 00. Oh, it's already 4:30. Okay, 0040123B. Okay, so we figured out. mm, 1 second, I got a bit confused. Okay, I messed up a bit. Sorry. Yeah, my bad. This is 1 byte, this is one more byte, this is, yeah, and then this is the next byte. So, my bad, really sorry. Yeah, we still are at, yeah, that was like the only issue. Okay, so we're here at address plus 2, so 2 bytes away. Yeah, we're here and we put in 64 because 0x40 is 16 into 4 plus 0. Yeah, so 64. That's the number you want to add into this first part. Into the second part, we have this entire thing. So that would be b plus 3 into 16 plus 2 into 256 plus, yeah, 16, yeah, 16, no, 64, and then 1 into 16 cube, which is, no, what am I doing? 16 square is 256, my bad. Is it? Yeah, yeah. And this is 16 to the power of 3. Okay, just basically 16 squared and 16 to the power of 3. I'm sorry. Yeah. This is the number that we want to write there. So I'll quickly calculate this and tell you. Okay, so calculator. Sorry. So B is 11 plus, yeah, 11 plus 3 times 16 plus 1 into 6. Hmm? think it's 4667. Yeah, makes sense. Okay, so this is 4667. Okay, the thing is, we've already written 64 characters before that. So we'll just subtract 64 from this. So 4663. That's the number we're going to write. 4603. Yeah. So look at this first payload, 64, then there's 4603, and like that. Yeah. So this is manually calculating it. So we split the number like this and we did it. I didn't want to do that. I wanted to try dividing and all that. So I just added up whatever this part accounts for. Say there's some math here. Yeah. So 65536. That is, I think, 16 cube plus 16 square. No, when we do divided by 1000. Uh, Wait. Yeah, 16 to the power of 4, I think. Yeah. So that's just says like in a decimal number. If we have 5, 3, 2, 1, 0, and I want only till here, so we'll divide by 10 to the power of 3, right? Same way, we want only these numbers. So we'll first floor divide by 16 to the power of 4, and then we find the remainder of 16 to the power of 4. And that's what I've done here in the second case. So I found holidays through using pawn tool symbols, and then from that symbol, I floor divided by 16 to the power of 4 to get the first number, that is that 40 number, say 64 basically. And the second one, I found the remainder of that, and then I subtracted the first number from the remainder because we had to subtract 64 from 4667, right? So that's what I did that there. And yeah, so and because these are integers, I have to convert them into strings and then convert them into bit strings and all that. So that, yeah, so I convert them into bit strings, and that is the number that I'm passing before this. Cool. I'll run the exploit and I'll show you. Okay, I have multiple exploits. Bad day today. Okay. No, it definitely works. I don't know what happened now. Okay. Um. Okay. I can fix this now, but I have more to show you guys, so I think I'll show you guys that first. Um, yeah. So like this was one thing when we have our win function inside it already. Okay, that thing that definitely works. Something some issue with uh, I don't know. Like my laptop has less space, so it keeps deleting stuff randomly, and that's what happened last time. Anyway, okay. So one second. Yeah, the second one, system slash bin slash sh for okay. So if we don't have a win function in our binary itself, I'll show you an example. Save this. Yeah. So say this is our example, and okay, you know what? I'll take you through a write up, which I don't have the link of right now. Closed. Uh, okay, I'll explain it to you. So hash include, yeah, okay, this is just my C program. Have a look at it. I am just putting, printing two lines and then creating a buffer, then again, taking three reads and having three format string vulnerabilities, three of them, and I'm taking it into the same buffer. This is just an example. Yeah. So what I want to do is I don't have any return like win function within this code. There's nothing. This is all that's there. What I have to do is I need to leak an address of libc from something that has been called twice. So puts has been called once, or like even if it's called once it works. It's called twice. So here, if through this format string vulnerability, if I can somehow leak the address of the libc of puts, I get the address of libc of puts, because and if I know the version of libc, because I have ASLR on for libc, I can find the offsets, and using offsets I can get the thing for system also. So then I find the actual address of system in libc with ASLR with the offsets and all that. So I find the final address of libc. Okay, the second format string vulnerability I'll use to overwrite something. Say I overwrite printf because I'll tell you why again, but okay, look here. Printf is being called and there's some input that's going to be passed to it. So in my third one, say I pass the input slash bin slash sh. I pass that as a string. And in the previous step I convert printf to system. Like the printf address in the GOT table, I now change it to system address. Then it's going to spawn a shell here, and I win. Yeah. So so now I have to figure out how to print values onto the stack. Fine, printing you figured out with the previous one. We need to find out how to leak values. That's something special, and as I told you, we can do that with percentage %s. Now, um, so my thing got updated, and I have to open WhatsApp. I'll just okay. I don't want you guys to see this actually, so give me a minute. Yeah, got it. Yeah. Okay, so this is a really cool write-up. Um, I'll take you to the main part of it, the most interesting part that we used for leaking. So writing, I showed you in a lot of detail. How do you write? I'm sorry, it's not working right now, but it works. Like I solved that question, so it really works. I bad day, yeah. So yeah, coming to the writing part, leaking. Okay, so here, yeah. So they're gonna leak something from Lipsy. They do that with percentage S. So the payload they put something some kind of an entity like and then L just also L just and R just this is left adjust. So they basically add more bytes to it to the left of the string that's being passed. This adds more bytes to it to the right, and then something and then they place an address on the stack, and they're using person they basically place an address say of puts at got.plt on the stack. Okay, and then with on a certain position, I figure out what position that is, and then I point my percentage s to that position, to this address on the stack. It now doesn't read the value which is there on the stack. It reads the actual address present on the GOT table. So that's how I can leak the values. So once you leak the values, then I think you know the drill. We have to go figure out if ASLR is on. All our addresses of libc will have a weird offset. Yeah, all of them will have that offset. We need to figure out that offset. So there are functions in pawn tools which helps you figure out. So it you can also open your own libc file through pawn tools and then make that also into an elf file, and then with that elf file you obtain the symbols, you obtain all the addresses of libc without any offsets. Like considering 0 as the base, you find all the addresses of libc. You have puts address, and now you have your actual puts address in this particular instance with that ASLR on with the weird offset, weird base puts, and then you have 0 base puts. You subtract it, you get that big offset, big weird address base offsets. You find the base address, and then to that you can again add your system with zero with 0 base. Then you get the weird base system address, so that's how you find the system address, and then you write that down with the same division of with the same way I showed you in this one, floor divide and remainder divide with 16 to the power of 4. You can figure out how many bytes whether you want to split it into 4, 2, whether you want to split it into 2, 2, like that. You can figure out and divide it accordingly and create your payload for writing. Okay, so that's how you could exploit this thing. Yeah, I think that's the idea. So um, So this percentage S thing is pretty cool. I took a long time to find it, and yeah, I'm really happy I did. That's it. You guys have any doubts? If you want, stay for 2 minutes. I'll try fixing my Python and seeing if I can run that. Otherwise, I'll let you know and you guys can leave. Okay. Then if you have any doubts, put it on the chat. Oh no, you guys may leave. It's not able to, like, I don't have space again. So it's not installing. Okay. Yeah. Thank you for joining.